Hello, everyone. I'm very pleased to welcome Professor Yuguang Zhang, who will give us a talk. The title is Adiabatic Limits of ASD Connections on K3 Surfaces.
Okay, so thanks for inviting me to give this talk. And here's the title. And the talk is based on a joint work with Data and Jacob. So first, let me say something about the background. So we consider this electromagnetic field on R4. So we consider on R4, we think about the Euclidean metric, give Euclidean metric, or as the Minkowski metric, sometimes with a minus sign. And the field is just a two form written in this way. EI, they are electro field, and the BI magnetic field, right? So in this talk, actually, I use the Euclidean metric, and the potential is one form, is A, and dA equal to F. So this one, and the F satisfies the Maxwell equation. So dF equal to 0 and the d star F equal to 0. The star is the Hodge star of the background metric. So the mathematical interpretation of this electromagnetic field, actually, we should interpret A as a Yuguang connection, and we put the delta equal to d plus IA. This one, this delta actually is a covariant derivative, and F is the curvature of this Yuguang connection, i.e. F equal to dA, which satisfies the Maxwell equation. And so you look at the equation. Actually, this Maxwell equation is just the equation for the two form. But furthermore, actually, we want to interpret this two form as a curvature of some connections. So so this is because we want to consider the gauge change. Let's say G equal to e to the I theta. The theta actually is a function on R4, and we need this delta, this covariant derivative, it change under the gauge change in this in the following way. And after the calculation, we have this A change under the gauge change in the following way: the A plus d theta equal to the after the change the A prime. And when we calculate the curvature, so the curvature actually does not change because here is d double d theta, so equal to 0. So why we want to interpret this thing in this electromagnetic field in this connection and the curvature language? Because the following: if we consider the Schrödinger equation, let's consider this capital phi. This thing is the wave function. Let's say describe some, let's say, electron, and we assume it's independent of the time t. When we consider the interaction between this particle with the electromagnetic field and the particle governed by this Schrödinger equation, and we need this whole equation is invariant under the gauge change, and so we need this derivative actually is a covariant derivative is changed this way. So that's the reason we want to interpret that equation for the Maxwell equation for the forms as actually is a curvature and connection, and also furthermore satisfy the Maxwell equation. Okay, so now we want to generalize about this picture, this connection. That's the Yuguang connection. We want to generalize to the high ranking connection. So let's consider this called the Yang-Mills equation. So now we consider the background metric is a 4-dimensional Riemannian manifold. and A is a SUN connection. Let's say we only consider coordinates patch in this Riemannian for manifolds, and this connection is over the principal SUN bundle. And actually, we can consider for any compact Lie group, but in this talk, I only talk about the SUN. So now n is bigger or equal to 2, and the A is a Lie algebra value, the one form, and FA is the curvature of this connection, actually written in this way. So in this higher rank case, so there's a nonlinear term pops out here. So it's not a linear, just a linear equation anymore. And the Yang-Mills equation satisfies the following equation. It's a generalization of this Maxwell equation. So d FA equal to 0, and the d star FA equal to 0. So this star is the Hodge star of the Riemannian metric. Okay, and actually this framework does come from this physics. So SU2 actually related to the weak interaction, and SU3 related to the strong interaction. And you also have the SU5 and something in physics. Right? So now, furthermore, we consider this called the anti-self-loop connection. So that's in the title of the talk. So in the four-dimensional case, in the four-dimensional Riemannian manifold, we have a special feature of this Hodge star. But Hodge star acting on two forms, the double Hodge star equal to 1. So this anti-self-loop ASD connection is the following equation. So with acting the Hodge star equal to minus F. So that's our anti-self-loop equation. So this thing obviously satisfies the Yang-Mills equation. You have the F, they are actually equal to each other, right? And the relationship between this ASD connection with the general Yang-Mills equation is as the following. So we consider this functional. It's a Yang-Mills functional, and the Yang-Mills connection is the critical point of this functional, and the ASD connection actually is the minimal point of this functional. And by Chen-Wei theory, actually, if this one is ASD connection, this one is just the second chain number of the principal bundle. So now we further assume that X is a Kähler surface, and in real dimension is 4, in complex dimension is 2, and we fix Kähler metric. So we have additional assumption, and we consider a principal SUN bundle over this X, and we use the standard representation of SUN. We end up a C infinity Hermitian vector bundle. So because this one is SUN, we take the determined bundle, actually it's a trivial bundle, and also implies, of course, that implies the first chain class is 0.
So is this bundle a holomorphic bundle or just a smooth principal bundle?
Right now, it's just a smooth bundle.
Okay.
Right now, it's only a smooth bundle.
Mm.
Okay, so okay, you can give different holomorphic structure. I will talk about that later.
Okay.
Now it's the ASD connection on this smooth bundle, and actually this one satisfies this Hermitian Yang-Mills equation. So it actually is a Hermitian Yang-Mills connection. So this equation system, and this because it's Kähler, so you have a decomposition of the two form, and you have 1, 1 form, 0, 2 form, and a 2, 0 form. And this F20 equal to 0 actually induce a holomorphic structure on this smooth Hermitian vector bundle. We denote this thing as this capital V. And of course, we have another. This one is really related to the Hermitian metric. And once we have this Hermitian-Yang-Mills connection, this holomorphic bundle actually is omega stable. So that's in algebraic geometry sense. So which defined in the following way. So for any Keller class, let's say also, yeah, maybe let's say ample class, a holomorphic vector bundle is called alpha stable. Or if for any proper subbundle, that's maybe it's the coherent subsheaf, let's say subbundle, satisfy the following equation. So the first chain class multiple this ample class divided by rank of this bundle smaller than this whole thing. In our setup, actually, it's just equal to 0. And we also can talk about the alpha semi-stable bundle. So in this case, it's smaller or equal, smaller and equal, right? So that's the definition for the stable bundle is totally in algebraic geometric sense. Okay. So the upside actually is, let's recall the famous result, the theorem by Donaldson, Winbeck, Yao. So if V is a holomorphic alpha stable bundle, then there exists a unique Hermitian-Yang-Mills connection for any calorimetric represent this alpha. So then we reach an equivalence between Hermitian-Yang-Mills connection and the stable bundle. This is called the Hitchin-Kobayashi corresponding. So notice this stable bundle is in the algebraic geometric sense, and this Hermitian-Yang-Mills connection is in differential geometric sense. So it's like this corresponding is like a dictionary. So you can translate from the algebraic geometry to differential geometry. And the differential geometry related to this, let's say the PDE, the Hermitian-Yang-Mills anti-self-do connection, Yang-Mills connection. And the algebraic geometry actually is this holomorphic structure. So it's actually sometimes more easier to deal with, right? So the question is, we want to study the adiabatic limits of the ASD connections. So let's mention some early works. So we have many this in the physics literature. People study this sort of limit. That's related to the dimension reduction of gauge theory. So for example, four-dimensional gauge theory reduced to two-dimensional, and many physics works, right? So in mathematics, we have lots of works actually, maybe not in recent year, but lots of this work. So for example, Salomon's work, Chen, Fu, Nishimo, also some other people actually many these works. So basically, in mathematics, this work actually related to the called Atiyah-Fourier conjecture. So let's look at one scenario. Actually, because there are many works and different works, I mean, they have some subtle different assumptions. Let's just look at a typical one. So typical one, let's look at this, for example, this X equal to two Riemann surfaces product together, and give the metric GT equal to G1 plus G2. And G1 is a remaining metric on sigma 1, and this G2 is a remaining metric on sigma 2. And we take a parameter T here. Then we want this parameter tends to 0. So we have this product. When T tends to 0, this sigma 2 shrink. When T goes to 0, actually this sigma 2 disappeared. So this thing collapses to sigma 1. And we assume the genus of this sigma 2 bigger or equal to 1. Actually, we just assume this one is bigger than 1. Right? Then we consider a family of ASD connection with respect to this metric of a principal bundle. And the expectation actually is this. This AT actually, when t tends to 0. So remember, t tends to 0, the metric actually shrink along the sigma 2 direction, and eventually converges to a holomorphic map from sigma 1 to the model space of flight connection on sigma 2. That's the, roughly speaking, is the idea Fourier conjecture. So the picture is, so this, how this work? The picture is something like this. So for any x on this sigma 1, we consider a fiber of this sigma 2. The AT restrict the sigma 2 when t tends to 0, actually converges to a flight connection on this sigma 2. And once this one is, the limiter is flight connection, then defines a point in the model space of the flight connection on the sigma 2, right? So now we change the x. We move the x along the sigma 1 direction, then this point actually gives us a curve inside this model space of flight connection, right? So that's the picture we want to demonstrate. So lots of work on this issue, all right?
I mean, this is only a conjecture. So this is a Fourier conjecture. So this corresponds when t is comes to 0.
When t tends to 0.
Yeah.
So this AT actually should maybe in some sense convergence to the holomorphic curve from sigma 1 to the model space of flight connection. So the full version of this conjecture, I think they have even maybe they have more things. So just this one is one feature of this Fourier conjecture,
okay.
right? It is probably not the full conjecture. So the full conjecture related to even the Fourier cohomology or something, right? So it's one feature of the conjecture. Okay, so now in our formal setup, we consider elliptic K3 surface from x to y, and the y is the base, so it's just CP1, and we'll assume the elliptic K3 surface. There's a section here, right? So the picture is something looks like this. So x and y, and we have a fibration, and we have some even singular fiber, and smooth fiber, they are elliptical curve, and we have a section, right? So for any regular fiber, actually it's a torus. So actually it's a elliptical curve. It's a C caution a lattice generated by tau. And we also identified this section, this sigma y equal to 0 here. Okay, so that's the elliptical our fiber. And we assume any fiber is irreducible, even the singular fiber is irreducible. So which means this fibration actually is a Weierstrass model. And then we fix the principle as U in bundle over X. And we do the twist construction, get a Hermitian C infinity Hermitian vector bundle. And then we consider each flight calorimetric omega t belongs to this ample class. So the alpha is ample class on X. We always assume this X is projective, right? So alpha 0 is ample class on Y. So we project alpha to the upstairs and have a parameter T product alpha plus this. So this one is also this one is a calorimetric. So now I want to recall the early result with Gross and Tossati. So our result says something like this, describe this flight metric. So when t tends to 0, omega t tends to a pullback metric from the downstairs, here. And over what? Over So we take a K, a compact subset over the regular part of this elliptic bundle. And we provide this K, and we get this shadowed area. So they basically cover the regular fiber. Over here, we have the C infinity convergence. And the omega is a calorimetric on the base, and which satisfies this equation. So the Ricci curvature of omega equal to the V-Peterson metric of the fiber. So remember, the fiber actually is a family of elliptic curve. So we have the well-defined V-Peterson metric on the downstairs, and we need the Ricci curvature of this metric equal to the V-Peterson metric. This equation derived by Zhang and Tian. And this thing is convergence. So what's the implication of this? If we look at the regular fiber, the diameter of this fiber, when t tends to 0, actually shrinks to 0. So it looks like the early case, the adiabatic limit case, so the product case, right? So let's our setup. And okay, so in this case, the omega t, actually this thing is called a hypercalorimetric. It's just not Ricci flat. And if omega denotes the holomorphic symplectic form, and we end up a hypercalar triple. So for example, we multiple some positive number of this omega t, then we consider the real part and the imaginary part, we end up this called the hypercalar triple. Then we have the hypercalar rotation. So the I is the original complex structure, and this one is the symplectic form. This one is a holomorphic symplectic form. Then we can change these three things. We get a different holomorphic structure. So for example, JT, and we use this one as symplectic form, and this guy as a holomorphic symplectic form, and KT, imaginary part of omega. Capital omega is symplectic form, and we have the holomorphic symplectic form. So in our original setup, we fixed the complex structure. We changed the basically we changed the Keller structure, and after right, and another thing, maybe there's some minus sign here, but I just ignore this detail. And after the hypercalar rotation, we can regard this thing as fixed symplectic structure and change the holomorphic structure because the holomorphic symplectic form actually changed. So it's a kind of a degeneration of the complex structures, right? So after this, so the hypercalar rotation, actually, the remaining metric, the corresponding Ricci flat remaining metric is totally the same. You just take a different point of view to look at the same remaining metric. So now, with that, this AT be the anti-self-do connection of P with respect to omega T, right? And then this anti-self-do connection actually equivalent to the following equation. So this double star equation. So this equation is good. Actually, it's what we prefer of the way to write down this anti-self-do connection with respect to some hypercalar metric, because this AT is obviously from this equation actually is Hermitian-Yang-Mills connection with respect to any complex structure. This hypercalar rotation, even after the hypercalar rotation, this JT, KT. Okay. So it's a should be called maybe hypercalar Hermitian-Yang-Mills. So now the question is, so when t tends to 0, what's the behavior of this AT? Okay. So our motivation of studying this question is actually related to this SYZ conjecture, but I will talk about that later, right? So it's not too much about this idea of Fourier conjecture. So first, now I need to talk about something about the technical detail. So let's look at the bundle on elliptical curves. So let's fix one elliptical curve. So let's say E equal to C cosine the Z2 lattice, which generated by 1 and tau. So for any point in this elliptical curve, we regard this point as a divisor. And of course, we have 0 point, that's the origin point of the elliptical curve, also divisor. Then these two divisor minus together, we define a holomorphic lamp bundle. And this lamp bundle, of course, is flat because this divisor is just 1 degree divisor minus together. So it's a flat lamp bundle. And actually, any flat lamp bundle we use this way, actually corresponding 1 divisor, 1 point on this E. So the modulus space of a flat lamp bundle actually is just this elliptical curve itself. So this is also the flat Yuguang connection. So you give a flat Yuguang connection, you induce a flat lamp bundle. So it's the same thing. Then let's recall. So let's recall a theory by Adia. This theory about higher ranking bundle. So for any semi-stable bundle V on this E, so let's assume the determined bundle is trivial. So in this case, of course, I say semi-stable. That means first, that means holomorphic, then it's semi-stable. Then we take the determined bundle is trivial. And this bundle is always looks something like this. So it's the sum of bunch of this flat bundle tensor, actually non-trivial bundle of rank Rj. And we take this Rj, take the sum together, is the rank of this bundle. Okay, so that's a classification result for the semi-stable bundle over elliptical curve. And we call this this semi-stable bundle is regular if this divisor, this Qj does not equal to Qi, if I does not equal to J. That's called a regular.
There's no condition on such a tensor product. So for a large bundle, what's the notion? L or J. So it's just any vector bundle.
This one? No. Yeah. This one actually is let's say rank 2. If we use rank 2, this one is just an extension of 2 trivial bundle.
I see. Okay.
So then you higher rank, you take the sequence. So first the extension of 2 trivial bundle, you got a rank 2. Then you extend this guy with another trivial bundle, you got a rank 3. Then you got the reduction.
Okay.
So it's just some non-trivial bundle.
Okay. I see.
I don't give too much detail there. And implication of this thing is V actually so-called S equivalent to this bundle. So without let non-trivial bundle, so equivalent to this one. So this this bundle actually is a flat bundle. So because it's the sum of bunch of flat lamp bundle, so this one is equivalent to this flat bundle. So this V itself may not be a flat vector bundle, but is equivalent in algebraic geometry sense. Basically, you change the holomorphic structure, take the certain limit in algebraic geometry, and you end up with a flat bundle. And then because the determined bundle is trivial, so we have this divisor. The divisor actually is in a linear system, the n times the 0. So this 0 actually, this big O actually is the original point of elliptical curve. So the divisor actually belongs to here. So then we consider the linear system of this n0, which is just a CP n-1. So it's equivalent to S equivalent class of semi-stable bundle with the determined bundle trivial. And of course, on an elliptical curve. And this one equivalent to model space of flat SUN connections on this elliptical curve. This because this holomorphic bundle, so the flat SUN connection induce holomorphic structure. It looks like this, okay? Because and also it's flat. And if we study directly the flat SUN connection, the model space. So what this thing looks like? So this thing is really looks like we take n-1 copy of the elliptical curve, then quotient a symmetric the symmetric group. So we end up orbifold. So as a symplectic manifold, we regard this thing as a symplectic manifold. This thing actually is an orbifold. So for example, let's take the n equal to 2. N equal to 2, what happens? So we have a elliptic curve, and n equal to 2. So it's just this thing is just the E, and we quotient the symmetry group of S2. So it's just Z minus Z. So we end up a sphere with 4 branched locus. So it's just the double. Actually, the map from E to this sphere is just the double branched cover. Okay. So here's the thing. So if we consider this gauge theory on elliptical curve, if we study directly use the symplectic geometrical point of view, study this model space of flat UN connection, actually it's quite complicated because it's not a smooth symplectic manifold, it's an orbifold. So it's lots of difficulty to dealing with this. If you, for example, you want to study the bubbling of a pseudo-holomorphic curve. But on the other hand, if we look at the algebraic geometry description of this picture, it's really the textbook, just a linear system. So it's a CP n-1. So it's as simple as it can be. So in our approach of this question, so we adopt this algebraic geometry point of view. So it makes things much easier. So that's the key point of this work. So now before we go to more detail, so we need another result. So this is called a spectral cover. So now let's go back to our setup. So we have an elliptic fibration of K3 surface, and with a section. Now we consider holomorphic vector bundle with determined bundle is trivial over this X, and for any generic fiber, regular generic fiber, it's semi-stable and regular. We assume this thing. Then from the above, this bundle, the restriction of this bundle comes with bounding a divisor in this linear system. Okay, so just a bunch of points. Then we actually, if we move this Y, the divisor, this divisor over this elliptic curve actually cut out a divisor of this X. So when we move this Y along the base direction. So notice if there's no, it's just a product. There's no this singular fiber things, and that's just the result. So we can have this, we can have a divisor in this X, but in this K3 surface case, more complicated. So we still have, then we need a big result. Actually, we still have the analogy the property of this. So we have this Friedman, Morgan, and Witten. So basically, the theorem says, so the first, under this setup, there exists the divisor belongs to this linear system. So sigma y is just this divisor, this section, and n is the rank plus m is a positive number, and this L is a fiber divisor. The fiber defines a divisor class on this X. Okay, so belongs to this one, and when restrict to the generic fiber, and the bundle looks like this. So you have this divisor minus sigma y, and this one is flat line bundle and cross some non-trivial, some this non-trivial extension. So it's exactly the same with this Atiyah theorem. And this divisor D intersection with this xy equal to this divisor corresponding to on this elliptic on this fiber, which is an elliptic curve inside this linear system. So it's a family version. It's a family version of this Atiyah theorem. So this D is called spectral cover of this V. Okay, so that's the definition. So what this spectral cover means. So once we have V, we have this D. Actually, the opposite is the converse is also we have a converse theorem. So for any this divisor, let's say reduce the irreducible effective divisor inside this linear system, then we can construct a holomorphic bundle with determinant bundle equal to trivial, and such that this D is the spectral cover of this V. Okay, and furthermore, so this thing is starting from this divisor and up this vector bundle. Furthermore, this V actually is stable with respect to some ample class looks like this for T. T is sufficiently small. So this ample class looks exactly like in our result for the least flat Cayley metric. So let's just really the coincidence we want to use, we want to explore for this case, right? So that's the offset. So one remark is actually not just this divisor D. So it's just assume this D is smooth. We can also put a flat line bundle over this D, and actually from this Friedman, Morgan, Witten's paper, actually two of them also we can construct a little bit different holomorphic vector bundle, but with the same the same spectral cover. So this D, of course, is you can choose this L in this Jacobian huge Jacobian torus of this D. Okay, so that's the Friedman, Morgan, Witten result. So this so this related to this XYZ Stromingo-Yau Zaslow mirror symmetry with bundle. So that's actually this is really our motivation to study this question. Okay, so what is this? So first we under our setup we use the hyperkähler rotation. Well, then our holomorphic fiber bundle actually become this so-called special Lagrangian fibration. And we take the dual fiber of this special Lagrangian fibration, we end up with this called the mirror of the original K3 surface. Actually, in our case, special case, because we assume this is a Weierstrass model, actually the mirror is totally the same. This X check is just as a differential manifold is original K3 manifold, and the fiber, the F check equal to F. So it's totally the same, so it does not matter. But with the mirror with the different complex structure and symplectic structure. And what this mirror symmetry says, this XYZ says, actually is a corresponding between the A model on one manifold with the B model on the mirror side. So A model basically consists the object, let's say, symplectic geometric object, let's say Lagrangian submanifold with some flat Yuguang connection over on this manifold. And the B model consists with holomorphic object, let's say holomorphic vector bundle, or let's say Hermitian-Yang-Mills Hermitian-Yang-Mills connections. And the slogan of this the slogan of the XYZ conjecture is this, let's say, Liang, Yao, Zaslow. So it says corresponding is the A cycles should corresponding to the B cycles. And this corresponding, the slogan is the XYZ mirror symmetry is this Fourier-Mukai transform. So from the A cycle is just the Lagrangian submanifold with flat Yuguang connection. B cycle is the holomorphic, let's say holomorphic vector bundle, or let's say Hermitian-Yang-Mills respect to something. We should have this corresponding. And then we have this Fukaya conjecture. So it's just one feature of this whole thing. So how do you get this this corresponding to the A cycle and the B cycle for the most general case? So we consider a family of this ASD UN connection. They are they are hyperkähler. I'm sorry. They are kind of like a Hermitian-Yang-Mills connection. And then we consider the adiabatic limit on this X. And the limit produce some A cycle on the mirror side. So this picture looks like a little bit looks like this Atiyah Fourier conjecture. Like you have an adiabatic limit of a family of ASD connection, and then you produce some submanifold on something. So this case is on the mirror side of this manifold. That's the Fukaya conjecture. Okay, so now I want to present our result. So what we have for this picture. Oh, right. So in our result, we present everything in holomorphic setup. So if you want this XYZ, you just use the hyperkähler rotation, then you can interpret this result as this Fukaya conjecture. The one feature of this Fukaya conjecture. Okay, so let's recall what we assume. So we assume this thing is an elliptic case surface with a section, and we assume any irreducible fiber. Any fiber is irreducible, and actually this whole thing is a Weierstrass model. And the alpha t is an ample class, looks like this. And then we find out this omega t is a rich flat Kähler metric. We fix the principal UN bundle over this X, and we use the twist construction, get a Hermitian infinity Hermitian bundle. And AT is a family ASD connections with respect to this omega t and the capital omega, which is the holomorphic symplectic form. So we write this ASD equation in this way. And the VT is a holomorphic bundle induced by this connection on this one. So as a topologically, all of this VT is this V, but with different holomorphic structure. So now we have our big assumption. It's a little bit of complicated assumption. Let's go through this assumption. So first of all, this VT, when restricted to generic fiber, is semi-stable and regular. The second one, then we have this once we have this, the first one, we have the special cover by this Feynman, Morgan, and Witten result. The dt belongs to this linear system. And because it's a linear system, when t tends to 0, of course, we have dt tends to a certain limit in this linear system. We assume this limit is something look like this. So you break to two parts. The first part is looks like exactly the same as above, but actually it's not. It's m prime. This m prime is smaller or equal to n. And the later one is belongs to the fiber class. So m minus m prime. So this d0, 0, d0 not or something. So we assume this one is reduced. It's a reduced divisor. And d0 prime consists of all irreducible components of d0 supported on fibers. So its picture looks like this. So this d0 prime is just a bunch of fiber class, and the d00 actually is still something looks like this, but this one is reduced. So we do not allow this d00 like a multiple. It's just a multiple divisor. So let's say n sigma something. So that's our assumption. So it's quite a complicated assumption. So how to once we have this sort of complicated assumption, so before I say the result, I need to say something about how to verify this assumption. So because this assumption is too complicated, so we can verify. Actually, it's very easy to verify this assumption. Actually, just use this Friedman, Morgan, and Witten's result. So starting point, maybe we starting point from this second one. We look at this divisor, this linear system. Once we take this m large enough, we can actually have this thing. Actually, is an ample class, and we can find out some effective divisor. Yes, in here, actually, we can even have this dt as a smooth curve, holomorphic curve, smooth divisor inside this x. And then we take the limit. Actually, we can just, just be lazy and just assume they are totally the same. We do not even take the limit. But anyway, we can, if we like, we take the limit. We have this one is easily to have because the structure of this divisor. So once we have this thing, we can use the second result. This the second result of this Friedman, Morgan, and Witten. So from this D, we can get some holomorphic bundle over this manifold, and actually less stable with respect to this ample class, also this Lich flat class metric. Then we use this Donaldson-Uhlenbeck-Yau theorem. We have our ASD connections, okay, and also because less stable actually is also a standard result by this Friedman. This thing actually is semi-stable and the regular. The regular actually come from this one is reduced. Okay, so it's quite easy to verify this thing. I just go backward. I wrote this result in this way. Actually, there's some because if I write this in this way, it covers more materials than just go back from 3 and go backward of this. Okay, so I can cover more result. Okay, so that's our assumption. So once we have our assumption, so what's the conclusion? The conclusion is, first of all, we can find out a Zariski open subset of this Y, and then we take the pre-image after a certain unitary gauge change. This take some sequence for any sequence tends to 0 by passing to some subsequence, and after unitary gauge change, this AT tends to a limit over here. The limit in the L1P sense, the P actually bigger than 2 to this limit. And what is this limit A0? The limit A0, the second, the limit A0 for any smooth point, restrict to any this smooth fiber. Of course, this belongs to this Zariski open set, which is actually smaller than this regular locus of the elliptic fibration. So they are flat and induces a holomorphic line bundle structure over here. Looks like this. So this Q minus this one is the origin of the elliptic fiber. And this Q, this divisor, is the intersection with D00. Belongs to this D00. This D00 is our the big component, this horizontal component of the limit of this spectral cover. Okay, so we have something like this. The picture it looks like this, the XY, and the Q is something like this. This D00 actually intersection with this fiber, and this one is the original part. Okay, so that's the our limit. So it's a flat connection, and the relationship with the spectral cover is like this. And that's the horizontal direction along the fiber direction. Then how about along the base direction? Along the base direction, actually we have the full the horizontal direction and the base direction. We combine them together. We end up with something like this. So there exists a flat Yuguang connection over this regular part, this D00 intersection with this. Oh, I'm sorry. This should be, it's a typo. It should be F minus this thing intersection with this one. So such that the A0 actually is the Fourier-Mukai transform of this whole thing. Sorry, this one is typo is F minus F to the minus 1, the pre-image of the Y0 intersection with D00 with this flat connection. Okay, so the limit of ASD connection basically it says the limit of the ASD connection is the limit of this spectral cover plus some flat Yuguang connection over it. Of course, modulate some bubbling. That's the component supported on fibers. Okay, so so if you want after hyperkähler rotation, this thing is exactly like A cycle corresponding to the B cycle of the limit. Okay, so that's all I want to talk about. Okay, thanks.
Okay, so thank you very much. Any other questions? So okay, since no questions, so let's thank the speaker.
Okay, thank you very much. Okay.
Okay, so would I ask? So is there some high dimensional? So for hyperkähler, high dimensional hyperkähler manifolds, is there a similar result or some expectations?
The problem is the gauge theory part. Let's become more complicated.
But the gauge theory, as you say, so there's a Donaldson and holomorphic Yau theorem still holds. So if you have some Hermitian-Einstein connection,
yeah.
connection.
Then when you do that, you got a bunch of bubbling stuff. That's really complicated.
So you mean the bubbling?
Here the bubbling is just a point, you know, and
yes,
we have 3 types of bubbling, so quite understandable. But in the higher dimensional case, you also adapt the base dimension of the vibration, also higher dimensional. Then you end up bunch of bubbling problems.
Oh, I see. This is a key point, maybe. Okay.
Okay.
Thank you very much.